Dragon's Gambit. Strategic Intelligence Analysis, Episode 2. The Rare Earth War, How China Weaponized the Periodic Table, and What It Takes to Break Free. Analytical Framework, Open Source Intelligence, USGS Data, DOE Reports, Academic Research Date, June 2026. On April 4, 2025, with 72 hours notice, China announced export controls on 7 categories of rare earth elements and permanent magnets. The announcement was 4 paragraphs long. The consequences touched every F-35 fighter jet in the American arsenal, every Tomahawk cruise missile, every Virginia-class submarine, every guided munition in the U.S. military's inventory. It touched the electric vehicles being manufactured in Michigan, the wind turbines being installed off the coast of Massachusetts, the smartphones in every pocket in America. 4 paragraphs. 72 hours notice. And suddenly the world's most powerful military realized it had quietly, over 3 decades, handed its adversary a veto over its own weapons systems. How did this happen? Who made these decisions, and why? And most importantly, can it actually be fixed? Today we go inside the rare earth supply chain. The geology, the chemistry, the economics, the politics, and the specific, unglamorous, expensive work of breaking free from a dependency that took 30 years to build. This is Dragon's Gambit, Episode 2. The Rare Earth War. Let's begin. Part 1. The 17 elements that run the world. Understanding what rare earths actually are, and why they're irreplaceable. Not rare. Not earth. Entirely indispensable. The term rare earth elements is, in both its words, somewhat misleading. These 17 metallic elements, the 15 lanthanides plus scandium and yttrium, are not particularly rare in the Earth's crust. Cerium, the most abundant, is more common than copper. Even thulium, the least abundant, is more prevalent in the crust than gold. The rare designation comes from 19th century geology, when these elements were found only in unusual mineral formations and proved difficult to extract. The second word is equally imprecise. Earths was the 18th century chemist's term for metal oxides. These materials were simply earths that resisted chemical reduction by the methods then available. What they are, precisely, is a group of elements with unusual electromagnetic properties arising from their electron configurations, properties that make them uniquely suited to applications in magnets, phosphors, catalysts, and electronic components. And here is the critical fact that makes them genuinely strategic. In most of their applications, rare earth elements cannot be substituted by anything else without significant performance degradation or fundamental redesign. You cannot make a neodymium iron boron magnet, the most powerful permanent magnet known, without neodymium and dysprosium. You cannot replace them with iron or aluminum and get equivalent performance. You can design around them, with sufficient time and investment, but the resulting system will be larger, heavier, less powerful, or less efficient. For military applications where size, weight, and performance specifications are not negotiable, these substitutions are often simply not available. This is what makes rare earths strategically different from most commodity dependencies. The 17, and what each one does. Neodymium, Nd, and dysprosium, Dy, the most strategically critical pair. Together they form the basis of NdFeB permanent magnets, used in the electric motors of every electric vehicle, every wind turbine generator, every hard disk drive, and critically, the actuators and guidance systems of precision-guided munitions. A single 35 contains approximately 920 pounds of rare earth materials, heavily weighted toward neodymium and dysprosium. Each Tomahawk cruise missile requires rare earth materials in its guidance system. Each Virginia-class submarine requires them in its propulsion and sensor systems. Lanthanum, La, and cerium, Ce, catalysts. Lanthanum is used in fluid catalytic cracking, the process that converts crude oil into gasoline and diesel. Virtually every petroleum refinery in the world depends on lanthanum-based catalysts. Cerium is used in automotive catalytic converters, in glass polishing, and in phosphors for fluorescent lighting and displays. Europium, Eu, terbium, Tb, and yttrium, Y, phosphors. These elements produce the red, green, and blue light in LED displays, fluorescent tubes, and energy-efficient lighting systems. Every screen you're looking at, every light in a modern building, likely contains these materials. Praseodymium, Pr, used alongside neodymium in high-strength magnets, and in aircraft engine alloys where it adds strength at high temperatures. Samarium, Sm, forms samarium cobalt magnets, an alternative to NdFeB with better high-temperature performance, used specifically in military applications where operating temperatures exceed the range of standard magnets. Gadolinium, Gd, MRI contrast agents. The medical imaging infrastructure that diagnoses cancer, cardiovascular disease, and neurological conditions depends on gadolinium compounds that have no effective substitute. Holmium, Ho, and erbium, Er, fiber optic amplifiers. The Internet runs on fiber optic cables that use erbium-doped fiber amplifiers to boost signals over long distances. The global communications infrastructure has a rare earth dependency that is essentially invisible to its users. Thulium, Tm, lutetium, Lu, scandium, Sc, specialized applications in medical lasers, solid-state lighting, and high-strength aluminum alloys for aerospace. The cumulative picture is a set of 17 elements embedded in essentially every advanced technology system humanity has built since approximately 1980, and concentrated, in terms of processing, in a single country. The chemistry that creates the choke point. Here is the specific technical fact that most political commentary on rare earths misses entirely. Mining rare earths is difficult. Processing them is exponentially harder. And it's the processing that China actually controls. Rare earth elements occur in nature almost exclusively as mixed oxides, multiple elements combined together in the same mineral deposit. Separating them requires a series of chemical operations called solvent extraction, dissolving the mixed or in acid, then using organic solvents to selectively extract individual elements through hundreds of stages of liquid-liquid extraction. This process requires specific chemical expertise accumulated over decades. Uses large quantities of chemical reagents, many of which are themselves hazardous. Produces significant quantities of radioactive byproduct, because rare earth deposits almost always contain thorium and uranium. Requires processing facilities specifically engineered for rare earth chemistry. The environmental and regulatory challenges of rare earth processing are severe. The Mountain Pass mine in California, which has significant deposits, was repeatedly opened and closed partly because of the difficulty of managing processing waste streams under American environmental regulations. The Lynas facility in Malaysia faced protests and regulatory challenges over waste disposal. In Malaysia, the Lynas lamp plant was permitted only after extensive negotiation and with waste storage conditions that remain controversial. China, during the period of its rare earth dominance build-up from the 1980s through the 2010s, processed these materials in facilities with significantly different environmental and safety standards, externalizing costs that Western competitors were required to internalize. This was not merely regulatory arbitrage, it was a structural cost advantage that made Chinese processing economically unbeatable for any Western company competing on a market basis. By the time Western policymakers recognized what had been ceded, China controlled approximately 60 to 70% of global rare earth mining, approximately 85 to 90% of global rare earth processing and separation, virtually 100% of the world's neodymium iron boron magnet production capacity at scale,